For this lesson, we're going to be taking a look at the number of zeros that a quadratic function may have. And this seems like a bit of a strange topic. We understand that we're quite often interested in what the zeros are, but in this lesson, we're actually going to be focusing on counting how many zeros there are. And on initial consideration, that might not seem particularly useful, but hopefully I'll be able to convince you why this is something that's worth considering as we work through our examples. Now, as some review, and this should be familiar to everyone who's at a lesson like this, which is parabolas can have a different number of zeros depending on how the parabola is positioned. In this case, you can see the blue parabola opens down. It has a negative leading coefficient, and I can arrange that by the position of the vertex. I can arrange that so that I have two zeros if the vertex is above, or with this red parabola which opens up, if the vertex is below the x-axis, I can have two zeros. It is also possible, if I shift those parabolas, I can shift the blue parabola down far enough that the only place where it touches the x-axis is at one point, where the vertex is actually on the x-axis. And I can do the same thing with the red parabola by, in that case, I shifted it up to the point where the vertex was sitting on the x-axis. So in this case, we only have one zero. And if I continue that shifting process, where the blue parabola continues to shift down, now you can see the vertex is actually below the x-axis and the parabola opens down. We have no zeros. Or the red parabola has continued to shift up. The vertex is now above the x-axis, and because the parabola opens up and the vertex is above the x-axis, it has no zeros. So a parabola can have two zeros or two crossings of the x-axis, or only one or none. So now we get into the note. This is what I'd want you to be copying down into your notes. So as I say here, we're usually interested in the actual zeros. Where are they? But sometimes we only interest ourselves in the number of zeros. Now, if you're given your equation in factored form, well, that means you already have the zeros. They are presented to you, and just by inspection, you can tell how many zeros there are. So you can have a factored form that looks like this, where you have two distinct factors. And if these factors are distinct, let's just say x minus s and x minus t. I'll put an a in front. I have two zeros here, and they're distinct from each other. Or you can have a single zero where I'll say x minus r, but all squared. And so that means that both of the factors would be the same, which is why you end up with a perfect square. And so you only have one zero. This is the case where you have a single touching point on the x-axis, or the vertex is on the x-axis. Whereas here you have two crossings of the x-axis. If you're given vertex form, it doesn't take much more work than it does with factored form to figure out the number of zeros. Because you have the case, you have the parabola, if it opens up, then if the vertex is below the x-axis and it opens up, that's two zeros. If it opens up and the vertex is on the x-axis, well, of course, that's one. And if it opens up and the vertex is above the x-axis, that is no zeros at all. And we can have a similar situation or a similar line of reasoning when it opens down. If we have standard form, now you do have the option, if you're in standard form, you could, if it's factorable, switch over to factored form. You could use completing the square to algebraically change it to vertex form. But it actually turns out that if you recall the general quadratic formula, the portion of the general quadratic formula under the square root is known as the discriminant, and it is this expression, b squared minus 4ac. And it turns out that you can just inspect that portion of the formula, the discriminant, And you can get your information about 2 zeros, 1 zero, or no zeros. Sometimes we refer to that as the solutions, or sometimes we refer to that as the x-intercepts. If you're going to use this method where you look at the discriminant, you're always going to want to start with the discriminant equal to 0, and then you can explore greater than 0 or less than 0 either through substitution and investigation, or through an illustration using a graph or the sketch of a graph. And I will hopefully illustrate this for you in one of the later examples in this lesson. But let's start with some simpler cases. So here I'm asked to determine the number of zeros for each. And so in this case, quite clearly, the number of zeros is 2. It is in factored form. Each of the two factors is distinct from each other. So obviously there are 2 distinct factors here. Part B, it's in vertex form. A little bit more work required here, not a lot. First of all, let's identify the vertex. You could do this in your head. The vertex is at -2, 5, or sorry, -2, -5. I'm going to write it out and just do a quick sketch. And again, you could visualize this. -2, -5 means the vertex is somewhere over here. And we notice that we have a negative leading coefficient. And that means that this particular parabola opens down. And so again, either sketching it out in your rough work or just visualizing it, our parabola is going to look something like this. And so the number of zeros in this case, I'm sorry, I always flip back and forth between the spelling of zeros. One of them is from my childhood, but subsequently I have learned that the established or the accepted spelling for zeros in Canada is with no E. So the number of zeros in this case is 0. And then finally, we have standard form. And in standard form, we have -2x squared plus 3x minus 1. That's your A, that's your B, that's your C. And then we use the discriminant. The discriminant is defined as b squared minus 4ac. So I'm going to check using b, which is 3. So that's going to be 3 squared minus 4 times a, which is -2, times c, which is, I was about to write 1, but it's actually -1. 3 squared, of course, is going to just turn into +9. And then I've got a negative times a negative times a negative. That's 3 negatives multiplied together. That's going to give me an overall negative result. And that's going to be -8. My discriminant is 1. I don't actually care about that number 1. What I care about is the fact that my discriminant is greater than 0. And with a discriminant that's greater than 0, that tells us that the number of zeros is equal to 2. So if you're just being asked for the pure number of zeros, then you can just go straight to the discriminant or use one of these other methods. I think that should be largely a review for students who are in the grade 11 course. This should be something that you saw in the grade 10 course. Now let's take a look at maybe something a little bit more sophisticated, which is making use of once again, the quadratic formula, but in this case, not to count the number of zeros. So in order to do that, it might be appropriate, just a quick refresher. We've already made use of this, and I just want to remind you, first of all, what the overall form of the quadratic formula looks like, so that you know what I'm referring to when I'm talking about the discriminant, which is the part under the square root. And the reason why this tells us our number of zeros, the most obvious one is when we have no solutions. If this quantity under the square root is negative, we're being asked to take the square root of a negative number. And we know that that is not a permissible mathematical operation. And so that's why we have no solutions. We're not going to get a real number. when we try to take the square root of a negative number. If we have the discriminant equal to 0, so if this whole thing turns out to be 0, then we end up with an expression which is x equals negative b plus or minus the square root of 0 divided by 2a. But of course, the square root of 0 is just 0, so that just ends up being negative b over 2a. That's a single result. It's the plus or minus that introduces two possible results. And that's why if b squared minus 4ac is a positive number, then you could have a result which is negative b plus that positive number, and then you could have negative b minus that positive number. And that's where you get your two possible real solutions. Okay, so now we're going to take a look at probably something that's not a review and an alternative view on how we can make use of this. So notice that the quadratic function that I've given you here, we actually don't know the c parameter or the y-intercept. It's actually unknown. And the question itself wants you to determine what value or values of k are going to give 1, 0 or one solution. So the way that we're going to do that is using the discriminant. I wouldn't normally write these out, but I'm just going to make sure that things are really clear for when we're using the discriminant. Our a value is 1, our b value is negative 5, and our c value is this unknown k. You do have to be careful. Remember, it's ax squared plus bx plus c. So you also need to be considering whether there's a plus sign or a minus sign here in some of the more complicated examples. In this case, the k very nicely takes the place of c. Now, for 1, 0, okay, so if we want to have 1, 0, that means the discriminant is equal to 0. But the discriminant is b squared minus 4ac, and so we want that to be equal to 0. b is negative 5, and then we're going to square that whole thing. The negative is inside the bracket here. Minus 4 times a, which is 1, times c, which we've replaced with the variable k. Negative 5 all squared is 25, minus 4k equals 0. 25 equals 4k, and divide both sides by 4. I end up with k equals 25 over 4. So therefore, there is one solution when k is 25 over 4. So that is our answer to part A. Part B then says to draw a neat sketch to illustrate your solution. So in our solution, we now know our value of k. So f of x becomes, sorry, a little bit of a scribble there. It's x squared minus 5x plus 25 over 4. And I'm not going to worry about too much as far as detail here. I'm just going to do a sketch, but I definitely need to know that this parabola opens up. And I know that this 25 over 4 represents the y-intercept of the parabola. And so I'm just going to put on a very rough x and y axis there. I'm just sketching it. 25 over 4 is almost 6. Now I'm not going to do a scale, so I'm just going to put the y-intercept there. And I'm going to add in a little piece of extra information. Technically, you don't need this, but it's kind of a neat little thing, and it's going to help us do a better sketch here. There's not a lot of talk about what the b value means in ax squared plus bx plus c. We make use of it, but we don't really talk about it. And so I'm just going to throw in this little extra piece of information so you understand why I'm sketching it the way I am. The b value represents the slope at the y-intercept. That's kind of a strange thing, but what that's telling me is that at the y-intercept, as it passes through the y-intercept, the slope is -5. And I think I actually need something maybe a little bit steeper than that. And so the slope is -5, but we know we have, I was about to do 2 solutions, but what we just found was 1 solution. And so that's going to come down and touch the x-axis. And that's a pretty crude sketch. I'm going to make sure it makes contact right there. So there is our 1 solution, or our 1, 0. So with our y-intercept at 25/4, with a slope at the y-intercept that's negative. If you didn't know that, you could have potentially drawn your parabola over on this side, something like that, and that would be perfectly acceptable for this sketch, even though it's not correct. And as you can see, we can still draw it with 1 solution. So I just gave you that little extra tip, and if you use it, great, and if you don't, no one will expect you to use it, at least not in the short term. So there we have, draw a neat sketch. Well, I don't know how neat my sketch was. I drew a sketch, though, to illustrate your solution. Now, what happens if we go with larger values of k? Or what happens if we go with smaller values of k? What would be the overall result? So let's try to imagine that. So if we take a larger k, what does that mean? That means the y-intercept moves up. Because the 25/4 represents the y-intercept, if I increase that number, then my y-intercept will be higher. So on my graph, if I put it up there, if everything else stays the same, then what would happen is the parabola would be up here. So, sorry, I didn't finish my statement here. The y-intercept moves up, and you can see what is the result when that happens. Therefore, when we use a larger k, in other words, when we use a value of k that is larger than, what was it, 25/4? The number of zeros is 0. Or there is no solution. I think I like that better. Rather than counting number of zeros, I would rather you say when k is greater than 25/4, f of x has no solution, or zeros, if you want to think of it that way. And I think you can probably see where this is going. What happens if we have, and maybe I'll just switch colors here so I can use the same axes. What happens if I use a smaller k value? That means the y-intercept moves down. And so that would put the y-intercept, let's say, much closer to the x-axis. And now my parabola is the same shape. The only thing that's changed is the y-intercept. And now I end up with this. It quite obviously has 2 solutions. So our concluding statement there would be when k is less than 25/4, f of x has 2 solutions. And that's it for our example. I'm just going to jump back to a previous slide for a moment because I want to highlight something that I said before, and I want you to tie that in mentally to our example. That's why I say if you are being asked to make use of the discriminant in order to solve for something else, you want to start with equal to 0, which is going to tell you about 1 real solution. And then you can illustrate your solution and figure out, as we did here. Then, once you understand your scenario that describes 1 solution, you can then modify your parameters, which will allow you to modify your diagram and you should be able to come up with what's going to result in no solutions. In this case, it was greater than, and what's going to result in 2 solutions. In this case, it's less than. So I hope that's clear. Here is some suggested work from our current textbook. As you can see, I've denoted some of them in green. Those are the basic questions. I wouldn't start there. So these are your basics. I would probably start at 4. And then if you run into difficulty, if you don't feel like you're able to make good progress, then only then would I go back and try questions 1, 2, and 3. 1, 2, and 3 are really simple review from the grade 10 course. And that's it for this lesson.